Record. Okay, right. Uh, now it's 9:30. Let's start. So read this code. What's the output? What's the output? In the last class, we discussed how can we create threads and how can we create a process, right? This is the mix and together. What's this? Four, yes. For the process, full process. And this is the child process, right? This is the parent process. In the child process, it's create what? P thread. This is the libc API, the P thread. P thread create. It's create a thread, and then create the value. The value is 0. The global variable initialized is here. So what's the output here? And what's the output here? This is if PID greater than 0, it's a parent process. What's the value here? Okay. Think about this. The process and the threads are very important concepts in operating system. Okay. What's the output? Yeah.
Would it be 5 and then 0?
Yes. Because you see the runner. This thread will run this runner. And why it is a 5? The runner inside is changed to 5. But why here is the output is a 5? Because here is a if they're joining, this means this thread is permanent. Joining means that this thread already permanent.
So the child process has 2 different threads?
Yeah, the problem. The child process has 2 different threads. One thread is the process. The process doesn't have one thread, right? At least the one thread, the process can run. And the process create another thread. In this another thread, it change the value to 5. But every side, the threads share all the memory space of the process. In the thread, it changes the value to 5. So in this process, this value is 5. Correct? Understand? But here is the parent process. Let's see the output. Let's see the output. Is it output? Child is 5, parent is 0. In the parent process, it doesn't change. Parent process and the child process are 2 different memory space. Okay, keep in mind, I always explain this part. Child process and the parent process are 2 different memory space. What all that happen in the child process will never affect the parent process. It says the value is different here. But thread share the same memory space with the process. Okay. Clear here? That's the P thread. So the P thread, what's the slide show? P thread is not, P thread is supported by glibc. It's not supported by, remember, it's not the interface of the Linux. It's not a Linux API. It's from a glibc. It's the lib P thread SO. So SO is we'll say the file with the .so. SO is a dynamic link of Linux. We'll say 8. So 8 That is a static link. Okay. So in Linux, we use different extension names to figure out it's a dynamic link or static link. So what's the difference? What's a dynamic link and what's a static link? What's the difference? Why do they have two versions of PCI link? Anyone knows? Yeah.
We talked about dynamic link, meaning it's just a link to the library.
Yeah.
And then at one time
Good.
um,
Good.
it accesses it, whereas
Yeah.
static link, it takes a copy of where.
Great. So all knowledge we should organize our knowledge. So it's still so the libc here is this lib have two versions. Dynamic link, as I said, it's linked during running time. The good thing is this is widely used lib. The good thing is all of the process can share the same library. It don't need to have many copies. But this one is if you compare to this file has this copy. So every file has this copy. It's a waste of memory space. Well, when you load this program into the memory, it has a copy of this lib. It's a lib. Why? Why we must have a multiple copy? So dynamic link is here better. Okay. Let's go on. Okay, this is PCI examples. Like I said, PCI example. This one is this example is little easier than the code. So here I create a thread, and the PCI join is wait for the thread to exist. Here in this thread, it will this is runner is a pointer to a function. So in the thread will run this function, will summarize all of the doing some calculations in this thread. Okay, good. Let's go on. Okay, question one. Okay, we have some challenge question. How many unique process means different process? Okay, how many unique process? How many unique threads? How many processes created? How many threads created? This is important. I must say, this should be in the midterm or final. Yeah.
Would be 2 and 6.
Two process and six thread. Can you let's step by step. How many until here? How many thread and process?
1 and 1, 1 and 2.
One child process and this is one thread created. Okay, here this is one parent process and
Second thread.
second thread over here.
Each create a thread.
Yes. So remember here is not included the PID is 0 or greater than 0. And this line, both child process and parent process will run this code. Okay. This code, remember this code is both child and because I here never check the return value. Both the parent and the child will check this. We will run this. So they are totally okay. Draw the process tree. Process and thread tree is better. Let's see the tree. So P1 will create a T1. This is parent. Okay, this is the child process. It's a child process. And P2 will create the T3. And after that, the parent and the child will run the same code to create another process. It should be two processes, two for T2 and T4. Wait. So question? Good and good? Yeah. this is in your mind, it's never a single process, a single thread run. It's here, both are running here. Okay, good. This is little challenge ones. I feel everybody is good. Okay. Next one, the Linux thread. Eh?
Sorry, for the last one,
Yeah.
I'm not clear, so it, like, there's a child process,
Yeah.
right? And then it creates a thread, so there's two separate threads.
Yeah.
And then the child also, if it's not that, it says else if there's a parent process and another thread, so there's two more.
Yeah.
And then the last one is regardless of that, create a thread, so should it be 5 threads?
Four
Because that's
thread.
not part of either.
First thread. Here is here only says how many are created. First thread created. And because this is both the child process and the parent process will run this. Child process will create a thread. Parent process will also create a thread.
Yes, but it's not a unique thread, so regardless of.
It's unique. It's different. It's different. Unique means it's not same. It's different. Unique means totally different. Different. Okay, it's totally different. Okay, it's need time to adjust. It's different.
Sorry, didn't you just say earlier that each child process has to have at least one thread? And then if it creates another, that'd be a second thread?
So that's the third reason. So oh yeah, the child process has one thread.
Yeah,
Oh.
but then it's, I guess that command is implied when we create the child.
So the main process and the parent process already have a thread. It's already here.
Yeah,
It's already here. And the child process create a process. It will
so isn't that automatically a second thread? When you create that child?
Yeah.
And then it says then create another thread?
which one? Yes, it's a child process that have a one thread.
Yeah,
Order is one thread. It must have a thread as well. And I create another thread. Okay, maybe it's wrong. I will fix this later. I'm thinking about this. Oh, okay. I will think about that. P1 is already include one thread. P2 is also include one thread. But okay. I will check. Good question. And you can do some experiment to check that. Print it out something. Change the source code, print it out something. I never think about that. Okay, you want? Okay, do some experiments test. Let's go to the next topic of a Linux thread. As we discussed, the P thread is not the Linux API. P thread is glibc API. But how about the Linux implement thread? It's a little different. Linux don't have the concept of a thread because the Linux want to make everything simple. They don't want to make a concept of thread. It has a clone. It has a system called clone. Allow the child task. Oh, in Linux, it's called task to share the address space of the parent task. Clone is not copy. Clone means share the address space of the parent. So you can create a task that share the same address space of the parent. That's the same idea with the threads, right? And also, okay, you must have so many flags. File system is shared, it's the address, and the memory space is shared, it's VM, clone VM, and the signal handling is shared, signal handling. The set of open file is shared. Okay, so including so many details. The Linux has so many details. Okay, and here, and when you use it, you must here you must malloc a stack memory, and then use a system called clone. A clone. This is all of the symbols to clone the processor memory space, and also you must pass this stack this memory. Then you can create a task. This task is a thread. It's very complicated and has lots of details not hidden. Lots of details hidden. So the question here is that Why here it must create a stack? Now, why here we must create a stack? Why here must create a stack? So this Linux expose lots of details. It's a clone. It means clone the okay, clone what? Clone is share the address space. So this task will share the same address space with the process. Okay, and it must pass a stack. Why it must have a stack? Because you see, it doesn't share. The stack cannot share. Stack is used for function call. Function call. So stack. This thread was running, it have lots of function call. We're going to call this function, not other functions. Stack use the function call. So each thread will have a independent stack. And here, so that's why it called a clone so many things now. But it needs separate memory for stack. Okay.
I think a couple of weeks ago, or last week, we talked about how a file, a program has, like in the memory, it has a place for data, it has a place for.
Yeah, you remember that. It's a text, data, stack, and heap.
Right.
Yeah.
So when we create a stack here, does it create a big stack and gets a copy of everything into the new stack?
No. This is
Or just a new stack.
You see, this is a stack, malloc. This is the new memory. The malloc is the memory from the process heap. This is the malloc memory from process heap. You see? This is a Linux style. The P style is different. Linux style, it's a memory allocated from the process heap. This is a heap. And this task uses the heap, the memory on the heap as a stack. It must have an independent stack to store local variables and what function call. Otherwise, how does the task know where to go back to, where to store the function call? Okay, this because expose lots of details. Actually, this is a process. This is a process of how can we create a thread. Okay. With PID. Okay, this use Linux API, and it cannot run on Mac OS. Linux, even Mac OS has support most of the API of Linux. Some of not support. That's why sometimes we use glibc is better. So all the operating system, once it supports glibc, I guess it must support it. It can use the glibc libraries, but this one is not portable from Linux to Mac. Okay, that's why the P-thread is better. It has any problems here? We rarely use them, but we'll see that you should know. Yes. Okay, go on. Let's go on. Okay, implicit threads. So because let's say Linux the thread API is very hard to use. Some we easy to forget, make errors, lots of symbols. So we have lots of library to that's called implicit threads. Treat and manage our threads done by compilers and runtime libraries rather than the programmers. So the programmers, like a programmer, will never manage the thread. It's managed by a compiler and runtime libraries. Like the fire method. Fire method is
It's 5 methods explored.
what?
There's only 4 bullet points. It says 5 methods explored.
Oh, fire method is 4.
Yeah.
Oh, yeah, sorry. I removed some ones and I not want to cover in this lecture. There's too many things. Okay, I will fix this. Thank you. I only cover fork join is thread pool is maintain a pool. Let's put all of thread in. As we not discuss here. And the fork join is also a model. how can we manage all the threads? And OpenMP, this is widely used. I always use this one. This is simple to use. I know that's okay. Next time I will fix it. Okay, let's say OpenMP. That's I always use this for parallel computing. This is a compiler already support this C++ function, and it's a provide a parallel programming shared memory environment. Shared memory means this is the main process, and it is the main process. It's a sequential code. Until here is a sequential code. Here, sequential code. Until here is sequential code, and in this paragram OpenMP parallel, this will compile the compiler for this. This will be compiled as a parallel version. And it will assign to each of the core in a CPU. This is the parallel region. This is the printf is running in parallel. And then here the sequential call. So this paragram OpenMP parallel it is a macro. It's a macro. If your computer support parallel, it will compile as a parallel version. If your computer don't support parallel or you don't link the library, it will be compared to sequential. So your code will never make any change. Okay, next time you want to sequential version. Okay, just compile again. Okay, compile again. So it's good. This is in the compiler, it supports this. Okay, yeah. This is run the follow of the parallel. Follow the parallel. So what happened? What's this used for? So it's a follow. And it's OMP parallel for. So this follow will run in parallel. This is array add operation, two array add operations. That's the result put in the C. So this is the perfect scenario for parallel. Let's say this is a data parallelism. So the data they don't affect each other. Each of the AI, BI, and plus to CI, they don't affect each other. So next one, I plus one operation will never affect this one. This is the very simplest one and easiest for parallel. So let's say used for matrix. In the mathematics, we always use matrix. So the task will split to multiple CPU cores automatically, and then it will add them together for parallel computing. And don't create some piece thread. Okay, make it very easy to use. This is implicit. You never see some piece thread, but this library, this OpenMP library will create lots of piece threads. Okay, it's time to show code. I have some interesting code to show. OpenMP. Say this. Can you see clearly here? Oh, I make it larger. Yeah, this one. This is OpenMP. See here, it's printf. So this region is the parallel region. So let's see the output. So I compiled with GCC. Compiled the GCC, but the GCC don't support. So I changed to GCC 15 because in my Mac, when I use GCC is use another compiler. I must use GCC 15. When I use GCC, it's C-long. It's a Mac will use C-long. So GCC 15 it will use this pure GCC. So this is compile things. And what? What? Where is my code? Okay. 哎，oh, wait a second. Yesterday busy use the share memory eh, where's my code? Static link. See, pause.
We have another one, below the thing, when open it. So on your channel 4. There's another thing, open MP for adding to arrays, is that the one you want?
This thread, Linux thread, Linux thread. Oh, I may be, oh, Linux thread. Fork and join, OpenMP. Oh, yes. Oh, yes, here, it's here, right? It's here. Refresh and this. Here, I use the OpenMP to add in two arrays, like I said, adding two arrays. Adding two arrays, so it's code. So I have firstly, I have to show OpenMP get max thread, how many threads it has. And this is how many threads it has run in parallel, truly in parallel. And this is to parallel region, to show the total workers in the parallel region. So the environment, you see, the never see some p thread happens. So next part is I use this code to create series A, B, and C. A, B, and C, three arrangements. The size is really long, 10 minutes. 10 minutes. Default, this is default size. I can pass in the variables. It says argv1 is my variables to pass from outside. And I have a three arrays to doing the add operations of array. And this is the parallel region. Parallel region says the parallel OpenMP parallel for schedule static. For schedule static. This for loop will split into what? Split into multiple parts run in parallel. And I choose the scheduling method is static. Static means it's already split in compile time. It's not in running time. It's not dynamic. It's static. It's in compile the for loop. N can be have a 10 minutes. So 10 minutes. Before they 10 minutes. This task is split to how many parts? 8 parts. I remember I have 8 core in my laptop. So it's statically located 8 core. It run and then printed out the running time. Let's check. Okay, this is compile. This is how many data it has. 1 billion. 1, 2, 3, 4, 5, 6, 8, 7, 8, 9. So 90 is 1 billion, right? So we have the array size is 1 billion. So it is really large. And I compare that. Compare that. And during the compare, so say this operations. Dash F OpenP. That means it will link to this OpenP library. And if I remove that, it doesn't have any OpenP library. So it don't support. So it's compiled with sequential way. See here. I don't have a command to, so this is the sequential running or parallel running. I use this compile option. This is linked to the OpenP library. This is compared to parallel version. I have 8 core, 8 thread because my laptop have 8 core. 8 core. So it will run in parallel and the running time is 1.9 seconds. Second, this one is running sequential because it don't have a FOMP. You get it? So it's running. Let's run now. Hey, hey, why? Okay, echo. Let's try again. Oh, oh, okay. I know. It's because I don't have this OpenMP. I don't have this OpenMP library, so it gives some errors. So I should remove this part. I should remove this part. Oh, yeah, this part. Okay. Oh, still. What? Oh, I also should remove uh, this part. No. Okay, later I can try. Oh, why is hmm. Okay. It's better to fix here. So you here. Wait a second. It's almost come out. Oh, it come out. Okay, wait, because it's very slow. It's sequential. Slow. Oh, it come out. It take 3 seconds, same as my I test last year. You can have speed ups. But you see here, I have 8 core. Yeah.
So so you had the code already ready for parallel,
Yes.
but because you want to display sequential, you have to comment those things out.
Mm.
If let's say I write a code, but I don't know where it's gonna run after.
No,
parallel,
this is my
Is there ways to put if statements or?
Yes, it has a speed because this is not necessary for running for this algorithm. It's I use this to print out some information. I guess the OpenMP supports some compile macro. And if it not support OpenMP, it don't compile this. Yeah, it's used to show some info. It also can I think it's easy to fix. It's asked to be easy to fix this one. So OpenMP, the idea is if you not support OpenMP, it will not compile. Clear here? It's not compared to the parallel version. So my question here is why, how many speed up? And the parallel version is 1.9 seconds, but the sequential version is 3 seconds. I have 8 core. So ideally I should have 8 times speed up, correct? 8 core. The task split to 8 core. So ideally I should have 8 times speed up. Why it's so slow? Why the speed up is so less, 1.9 seconds? It should be 3 divided by 8. Why? Performance analysis. And okay, try your best to answer my question. So if you can try. If you want to try, man, just try. I want to make you think about this. I think about it. Time management. Okay. Any ideas? Why here is very easy. The speed up is so less. Okay, this is a really hard question. So I can explain that because you know, 8 times speed up is a perfect scenario, and we can never reach to 8 times because this OpenMP it need time to create the thread or create the thread and manage all the thread, split the task. All this need times, and more important, on my Mac it's running Zoom, running PPT. Maybe I have lots of things open on the background. They all cost the CPU resource. I don't close them. I directly run them. And also this is what the 2-bit lab. All this need need resource, need CPU computing resource. So that's why the speed up is so less. Right? 8 times the speed up is perfect. We can never reach that. But it's good to evaluate. So this parallel is good or bad? Good or bad? We must spend something for the parallel, like a speed task, create a thread. How can we manage this thread? All this need resource. That's called CPU scheduling. So the next chapter we talk about this. How can we manage all this thread? So here it's a balance. If it use 8 threads, okay, 8 core is good. But if we create too many threads, I think it becomes more slower. I create a 100 thread. It's more slower because I only physically have 8 core. 100 thread can only 8 thread can run in parallel physically, at most physically, because my computer has other things to do. So that's become more slower. So not more is better. Suitable is better. Okay. And another important thing is laptop is not designed for some high performance computing. This is the intensive computing. Fully use the CPU resource. The CPU will slow down. The laptop too hot, right? So any questions here? It's use OpenMP, and we can go to the next topic. Chapter 5. CPU scheduling. We have a lot of threads, lot of process. But you see, my laptop only have 8 core, right? 8 core. So it must have some scheduler to manage them. 8 core means it can only have 8 processes run physically in parallel. If we have 1,000 processes, it must be reduced to what? It's still 8 can run in parallel. That's need scheduling. So the basic concepts. I remember we discussed this before. So the CPU burst, loading, store, and CPU. iOS is almost operating system scheduling almost all of the resource to the system. CPU is the primary resource because the CPU is really fast, much faster than other storage like memory, disk, SSD. SSD is much faster, right? And disk. So CPU is much faster. CPU is a primary resource. Our scheduler is mainly working on the CPU. How can we fully use the CPU? For example, here, that's called maximum the CPU usage. CPU is so fast. Don't let CPU idle. Let CPU keep always busy. So keep always busy. So CPU is a burst. Loading, store, adding, store, read from the CPU burst. This is I/O burst. I/O burst. I/O burst means the program start to read file to disk. It's very slow. Now CPU is just waiting for I/O. CPU is wait. So here CPU is waste his computation. CPU is a primary resource, but there is a waste here. So the next time the CPU burst, CPU is busy, and then it's waiting for I/O. Okay. And something. Doing some calculation, writing to file. Doing some calculation, writing to file. It's a very CPU is always waiting. So the scheduler means during this period, so we can load in other tasks. We can load in other tasks. CPU can switch to other tasks, continue the computation. Good here. So this is the pattern of cycles of CPU execution. The CPU will always busy calculation and then wait. So here, this is a burst duration. This is the burst duration. So this is the CPU. So for one process, the CPU running time, and this is the frequency. So you see, when the duration is short, that means that this program only run like 1 or 2 milliseconds, very short. It's so many threads, very high frequency. So many threads have this short running time, but until here, this process takes a really long time, like 1 second, only 1 or 2, 1 or 2. So this is the important pattern for CPU running. Most of the threads or process are very quick to run, and only several of them take a long time to run. Our scheduler is based on this observation. This is from our daily using computers, not for some server. The server may have some specific task. It's different. Okay, this is for mainly purpose using our laptop, desktop. Lots have different kinds of process and threads. We also have this one. The large number of short burst and small number of long burst. Good here. And the next, primitive and versus non-primitive. Non-primitive scheduler means a running time task is executed until it's complete. We never interrupt it. So the process come, it will run until it finish. It cannot be interrupted. That's a non-primitive scheduling. Otherwise, the primitive scheduling is maybe it can be interrupt and move to ready queue. So the process is running queue is running. So my for 8-core laptop can 8 person can run at the same time. But think about this is a single core. Single core means only one thread can run at a running. So the primitive means the process is running and it can be interrupted and moved to ready queue. It's not finished. It's not yet finished. But some high priority process or thread come, it's been moved to ready queue. And once once it's ready again, it moved to running again. So it's a primitive. So virtually all the operating system, Windows, Mac, Linux, Unix, use the primitive scheduling algorithm. Can we have an open discussion about why modern operating system is primitive? Using your common sense to ask common sense. Let's discuss 1 minute, and then we can come back then 10 minutes later. Take a break. Yeah. Take a break. Okay. Yeah. Yeah, that's oh, I have 3 minutes. 2 minutes left. Good, that's back. Okay. Back to our question. So why the modern operating system use the primitive schedule? Any comments and to say something? Let's say something 1 minute with your neighbors. And then we can try. That's a try. I know you may don't have enough background. Let's try. But that's why how do you use your comments? Just we use our operating system every day, or the cell phone, laptop every day. Why is it primitive? Why is the modern of this primitive? Okay, right. That's all. 1 minute for discussion with our neighbors. Okay, know your neighbors. Discuss with your neighbor 1 minute. And try to answer our questions. Why is more than talking about why you have to instead of in pursuit beyond the place. Order for us to do it. And I'm going to allow slides to be forward here. Offers we may go class. And you have it up. Good. Who can answer this question? Right. Right, yeah. Why modern operating system primitive system? Why do we also? But I know primitive is must be more complicated than the non-primitive. So why is more of a why? Okay. I need the new ones to answer the question. Yeah, please, right? Please, right? Yeah.
So we discuss, or we feel that it's because it's more efficient.
For what? Efficient for what?
Because, you know,
Right, not matter. This is what not matter.
well, I mean, like, because the previous one, there was wait for just waiting for like the to move things from memory to whatever, you know,
Okay, I got it.
Is it to price conditions? Is it to prevent price conditions?
Yes. Not really. Anyone? Last one. Right. Yeah. Right. Last one. Yeah.
Isn't it also because that if there's any errors when running coder program and then the preemptive you can and terminate the task and then reboot it? Or would that be wrong?
Not really. Not really. So you know primitive. The benefit of primitive is quick response. Think about the one process that really has taken lots of time. And it takes all the CPU first. But other emergent process come. So the CPU must be quick response, low latency. So which application need quick response? Your operating system. Like our UI. Like our cell phone, like you don't want to stop, right? You don't want the UI stop. So this is high priority. If someone takes CPU, it must be primitive when UI need to respond. So that's right. That's why the modern operating system is primitive. Otherwise, some of the tasks take like 1 second. It take all the CPU resource. Your computer sees the freeze. But from our human, the screen freeze means the computer freeze. The UI freeze means computer freeze. So primitive response, we need quick response, real time response. We don't want our playing games and freeze. That's the primitive. That's the most important.
So isn't that also the reason why there are some applications on laptop computers may have a priority on what resource to make?
That's the priority scheduling. That's the priority scheduling. Priority scheduling, it must be primitive. This task is very take a long time. If other one have higher priority, it must be primitive for it and it can go. Yeah, if it's not primitive here, it only comes the exact until it's completed. For primitive research. Primitive response. Good. Good, you know. This is you're using your concept to say primitive and non-primitive scheduler is here. Also, one processor is running, right? One processor is running here. It is running only half of that. And it is stopped and save the state. And you know the PCB. Save the state to PCB and move back to the ready. That means primitive. Non-primitive is means when it is wrong, it will not be completed and going to be terminal, and then pick up another ready process to here running. Okay, so let's say more details. The CPU scheduler. CPU scheduler select from among the process in ready queue. Select in ready queue and allocate a CPU core to one of them. CPU core to one of them. Once a process must have a CPU, physically have a CPU core, it can run. Right? Allocate the CPU core. If it is 8 core, so 8 thread can run at the same time. So here one process may have many threads, thousands of threads. So the unit running on the CPU is the threads, not the process. Threads. Okay, here. So, but sometimes I always here use some process. But in your mind, it's one thread can run on one CPU core physically. Right? Two threads must be run in two cores physically. It's impossible to run in one core. If you're running on the one core, two threads must be reduced to sequential. You do first, I do later. Reduce to sequential. Okay. So queues may be ordered in various ways. So you have two queues. This is the ready queue. This is the waiting queue. The queue is increased by what's the data structure like this? What's the data structure? Is it the PCB? PCB is the process. Save the state into the PCB. Process can do what? PCB. And also save the resistance. All the status, the information stated here. So this information used to restore to this state can be wake up. So like that, this process or thread is sleep here, and it can be wake up during running. So what's the data structure used here? I suppose you know that in the data structure course. Just yes. Yes, single unit. You can double link this limit, but here so in single unit. It has had a new is singly linked because why the single, because we want to get one from the hat. Get one from the hat. Okay, it's a single. We don't need to delete someone in the middle. If we want to delete someone in the middle, we must use the double linked list. Here is a single linked list. We only need to get one processor from the head, get one PCB from the head. Okay, so CPU scheduling decision maker one process. It's the first scenario. The first one is switch from running to wait. Running to wait is because of the IO. is this process want to read and write files. It's very slow. It's too slow. Let's put it into waiting. And sleep here. Put it waiting. Sleep here. IO event wait. That's all. Then it put into the waiting queue. And then next one, switch from running to ready. Running to ready is because someone interrupt. Interrupt like all of the things in the operating system, not in operating system like error handling, use interrupt. And the system call use a software interrupt. I will call some trap. Actually, it's an interrupt from running to ready. And the third one is switch from waiting to ready. From waiting to ready. So IO event complete. IO event complete from waiting ready. It must be take this PCB out and put into the ready queue. Put in the ready queue. And first one is the most simple and terminate. Running when it's complete, it's terminate. So where can we doing the CPU scheduling? Which process can do CPU scheduling? Okay, how about this one? Terminate. Why we terminate this? Why we schedule terminate, right? So the running process finish as terminate. It's nothing we can do. How about the first one? Running to wait. Running to wait. Running to wait. Can we do scheduling? No, because we don't know when the IO happens. We cannot predict the future. And when the IO event become, when IO event come, read or write files, it come to waiting. It don't need some scheduling. Well, it's naturally happen. We don't need scheduler. So the scheduler only can do is that, oh, okay. Scheduler only can do is 2 and 3 from running to ready. From running to ready, I think this interrupt is some software interrupt. We can dealing with later. Running to ready, and from waiting to ready, waiting to ready, waiting to ready, and the running queue, the running will take the first one from ready to execute. So the scheduler is the ready queue. How can we put a different place? If it is with higher priority, we can put into the head of the ready queue. So next one, we will go into execute. If it is not very important, we can put into the tail of the ready queue. Tail of the ready queue. Okay, we can implement this schedule. Correct? Okay, as I said, only the situation 2 and 3, we can make some choice. 2 and 3, we can make some choice. And for situation 1 and 4, there's no choice in terms of scheduling. So, okay, here. CPU. So all the scheduling happen in 2 and 3, or 2 and 3, let's back to again. 2 and 3 is from running to ready. Running to ready and from waiting to ready. It's only these 2 cases we can do in scheduling. Let's go on. Okay, scheduling criteria. So now, how can we evaluate our scheduling method is good or bad? We say our scheduling is good. We say that the CPU utilization. So CPU is a valuable resource, computing resource. Scheduling to keep the CPU always busy. And keep your CPU always. If the program, if the process is reading or writing file, IO operations, reading or writing files, let CPU do other things. Don't make them lazy. Always keep CPU busy. It's a major purpose, right? Major purpose, keep CPU busy. And through output, number of processes that complete the exception time unit through output, and turnaround time, waiting time, response time. Turnaround time is the amount of time executed a particular process. The turnaround time, the total time. Waiting time is the amount of time of waiting in the ready queue. And a good scheduler should have a minimum waiting time. Right? Why this app waiting so long time is not executed? That's a bad scheduler algorithm. So minimum the waiting time, minimum the turnaround time, and then minimum the response time. Like I said, the UI need quick response. So in total, one sentence, maximize CPU usage. Don't make it lazy, and minimize all the other time. Okay, we will discuss lots of scheduling algorithm uses maximize the CPU usage, minimize all the other times. Okay, we have 1, 2, 3, 4, 5. 5 important CPU scheduling algorithms. Okay, let's take the first one. I say it's important. Okay, important. This is a very first come first serve, most simple one, but it's I think it's important. I say it's must in the midterm or final, and also in the assignments. Right? Assignments. So processor requests the CPU first, allocate CPU. Oh, sorry. So it's in the first come or first serve. This P1 is the first come, so the CPU is busy. P1 is the first come, so the CPU will deal with P1. Then P2 comes, CPU compute P2. P3 comes, CPU compute P3. They don't have some complicated strategy, just first come first serve. Like it can be implemented as a waiting queue. Okay. And this is non-primitive. I guess the early age urban system use this one. Very simple to implement. And the non-primitive, the P1 must execute until it's terminated. Even if P1 P3 is so important, it cannot stop P1. So the response is not very good. If P2 is important, if P2 is our UI, response is not good. It's a non-primitive. And the CPU waiting time may be very long. So P2 and P3 waited so long time. So let's say how can we calculate the waiting time and the turnaround time every time? So this is the two analysis. This scheduling strategy algorithm. What's the waiting time? How can we calculate the waiting time? How can I calculate the waiting time? Okay, let's make an example. Let's make an example. And then waiting time is P1 is P1 don't wait. So it's 0. How about P2? P2 must wait. Here is P1, P2, P3 arrive at the same time at 0. Make it easy to calculate. So P1, P2, P3 arrive at the same time at 0. And P2 the waiting time is what? 24, because it must wait P1 to terminate. P3 is 27. Here, it must wait P1, P2 terminate. So the total waiting time should be, add them together. And the average waiting time should be divided by 3. So it's here. Okay. Until now, it's good. Until now, it's good. Let's say the average or average waiting. How about turnaround time? Turnaround time means the total time including the waiting time and execute time. So this process waiting is still counted for the turnaround time. And we will care about this total running time, like the turnaround time. So P1 is 24. P1 don't wait, and P2 is wait for a long time and until here 27 terminate. P3 is 30. Good. So average turnaround time is add them together divided by 3 is 27. So the question is this a good scheduling or not? Can we do better? Can we do better? So it's a waiting time is seems large. So average waiting time seems large, 17. Average turnaround is 27. So a better scheduler algorithm should be minimize this one and this one. Right? The CPU is fully used. CPU is good, fully used. 100% used, never lazy. Good. But this time is we can be do better. How can we do better? Okay, I think now you know how to calculate, because this time it's still first come first serve, But this time P2 come, also all the all the process come at the same time 0, but it pick up P2, P3 firstly, and then exactly the P1 secondly. So is this a better strategy? This time is good. It's not something. It's first come first serve. So this case is better than before this one. Okay. To answer this question, we must know what's the waiting time. What's the waiting time? What's the turnaround time? What's the waiting time? Good. 0, 3, and 6. What's the turnaround time? What's the turnaround time? Yeah, good. Good try. What number? Yes, 3, 6, 30. Good. The turnaround time including waiting. Waiting and exactly all is the turnaround time. Turnaround is the. So that's and average means divided by 3. It's 3. Average waiting time is 3, and average turnaround time is 13. It is what? Much better than last one. So last one is 1724, and this version is 313. Waiting time only averagely is 3, and turnaround time is averagely is 30. It's much better. Why is much better? Can you find something? Yeah, can you find something?
Order processes are done first.
Yeah, short done first. So the P1 can wait short time. If last example is the P1 done first, and P2 and P3 must waiting for a long time. And this waiting time is counted for turnaround time. Right? Turnaround time including the waiting plus executing 2 times. So P2, so short job firstly must be a good strategy. Okay. Yeah, that's it. Short process behind long process, resulting in lower resource utilization. And this is a good strategy. Okay, that's why we have naturally we have idea of short job first scheduling. Short job first scheduling. We pick a short job firstly, and then we execute the long job secondly. But the problem is so short job first using like a CPU burst scheduling process with the shortest next CPU burst. We always say next CPU burst because we cannot predict the future. This is important thing. Short job firstly is optimal. Like I said, it's optimal. It's optimal. It is the best. I say it must be the best strategy. But how can we predict the future? We don't know. How can you know that the process P1 takes how can you know that the P1 takes this long time? You don't know that. You only know after it's terminate. Right? This is the problem. How can we know the P1 takes so long time? If we know that, that's good. We can sort it that. Simple. But we cannot predict the future. So that's why I say short job firstly is optimal, but we can never implement it because we cannot predict the future. That's why shortest job firstly, maybe it's not a good name. Maybe shortest next CPU burst. That means we can only make a prediction of the next CPU burst. We cannot know the exact running time of next exact running time of this process. We don't know that. How can we know that? We cannot predict the future. So that's the question is that how do we determine the length of the next CPU burst? So like a P1, P2 running, how can we know that? We only can guess. Good guess or bad guess. We cannot know exact value. This is important. I say it's important. Okay. How can we guess? Okay. How can we make a good guess?
Maybe like a time complexity for processes, not like version, like you know how like the algorithms kind of assign a time complexity. You go try and apply that to the process.
Interesting, but I must say it's not a good idea. How much time you use for another time complexity? Is it a CPU scanning?
Well, I'm saying like apply something similar to that. I know this could be different. I'm saying
Yes.
apply something like that. Maybe
Because
you've run the process before.
you must
You
consider
keep a log of how long it could be.
you must consider CPU will do other extra work to analyze them. the first time. Okay. Good. We can make a prediction, but not always correct. And it's important to know the global information process in future. It's like I said, the time complexity. So we can know that. And you must consider about how CPU know that. How CPU know that. You see, this is in the bottom of the CPU scheduling. So it must be very efficient. Consider about how much running time CPU spend to predict the future. It's a balance. It's a balance. So here is we cannot know, but maybe CPU can know some global information. The global information. Oh, this process may be very long. I put into the end. Actually, so in a word, this is optimal. We cannot achieve that, but this is good to evaluate. Oh, this scheduling algorithm is good or bad? Is this close to SGF? If it's very close to SGF, it's good. If it is far away from SGF, it's bad. It's still meaningful to evaluate this scheduling is good or bad. Here, we can never reach this optimized result. But we can try and we can evaluate. Okay, let's make an example. I'll say the first time is we have a first round. First time is 6873. So SGF scheduling is we pick the shortest one to come. Shortest one come. Yeah. And this is sorted. What's the waiting time? What's the turnaround time? What's the average? What's the waiting time? Yeah. What's the waiting time? Yeah. Okay. Go on.
03916 for the process P4, P1, P3, and P2 respectively.
Yes. What's the turnaround time? Turnaround time is turnaround 3, 9, 16, 24. Right. Yeah.
Yeah, you said.
Yes. Good. So average is divided by 4. So this is the shortest job first. So they are sorted. So this is the optimized result. It's impossible happen in real CPU scheduling. Okay, keep in mind, impossible to happen. Maybe we can make a strategy very close, but impossible happen. Okay, good. All we just talk about is non-primitive, right? Non-primitive. Let's say the job P4 must finish. Then can run P1. The P4 cannot be interrupted. So it's non-primitive. But we always say the modern operating system is primitive. So all of this some first come first serve, and SGF has a version of non-primitive version we already say, and it also has a primitive version. Now we can add. Now we can use the primitive. Let's see example of a primitive version. So now this is the shortest remaining time first. It's not the shortest running time first, because this remaining time is after running this thread P1, after P1 running here, how many times is remaining? How many times is remaining? If P1 remaining is shortest, so it can be put to here. And if not, it must be put here. So it's primitive. So after each of the 0 to 1, it can be primitive. So and this example is a little complicated. Arriving time is different. All above example is arriving time is the same time. and the arriving time is different. 0, 1, 2, 3. And the burst time and also some P1 is really large. Say P1 is really large. And we know that P1 is a long time, is not a good idea put to the head. Not a good idea to put the head. It's make a long waiting time. So let's make this is the primitive version. P1 from here. And P2 primitive. Here, P1 is not finished. And the P2 come to P1 come to here. Because this is the shortest remaining time. Shortest remaining. This remaining time is 7. This is 7. And this is 5. This is 4. This is 5. This is 7. And this is 9. Right, 9. So it is it use a shorter remaining time. It's good. Am I explain like this? Good. So now what's the waiting time? What's the average? What's the waiting time? Okay. Okay.
What? I don't understand that the preemptive is.
Primitive. Primitive means the P1. P1 is the first time is 8, arriving is 0. Well, this is P1. But P1 can be interrupted into 2 parts. This means primitive. This means primitive. So P1 is from 0 to 1, and it is split 2 parts. So as P1 is here. And why we put P2 here? Because remaining time. P1 remaining time is 7 until here. Here to here is 7. So, but it's much larger than P2. P2 is only 4. 5 minus 1, only 4. And P4 is 5 to 10 is 5. P1 to here remaining time is much larger, is larger than P2 and P4, so it's put to here. But this is still smaller than it. This one. Get it?
Sure.
So this is remaining time. Remaining time is how much time I still need. Question?
How do you know the percent for
This one?
yeah,
I just said it's you can only predict and make a guess. This is optimized scenario, optimized case. You can never reach out, you can never implement. It can use to evaluate your algorithm is a good or bad. You cannot reach that. Oh, but you can make a guess that P1 may be very long. I can make a guess that it should be greater than 8.
if we guess we want to be like around 8, why don't we just schedule that for after before? Why don't we have to break it into parts?
And break it apart. Yes,
Yeah, but because we predicted like the processing time we want to be like around 8.
Yeah.
We could have just scheduled it for after before instead of like splitting it into parts.
schedule P4 instead of. Do you mean schedule P4 first name?
So the reason why you can do that is at time 0.
Yeah, it's arriving time is 0.
We want.
We don't want the CPU to.
You waste that one cycle.
Mm.
Okay, that makes
Right,
sense.
and everything goes to that one, so that one cycle is.
Good part. Good. So our purpose is maximize CPU usage. So P1 is calm. That's why that CPU lazy 1 second. Okay, lazy 1 second. So if you do P2 firstly, this is idle. CPU is do nothing. So maximize CPU usage and minimize all of some other time. So now how can we calculate the waiting time? Waiting time. P1 is split to 2 parts. How can we calculate the waiting time? I guess other is easy to arriving. Waiting time is burst time minus arriving time. P2 waiting time is 0, right? 1 minus 1. P2 arrive and execute. Waiting is 0. P3 waiting is P3 17 minus 2. P4 is 5 minus 3. It must wait sometimes. How about P1? P1 split to 2 parts. And its calculated waiting time is
because the first one is a zero, it doesn't matter if you're adding zero, so you can just use the second one, which is.
Second one is with 10 cents, 10 cents. Here we must minus this one because it's split two parts. It's already, this is not good, it's already like this. P1, waiting time. P1 is 0 plus 10. 0, P1, two parts. This part don't wait. And this part, wait 10 seconds. And it must minus 1. Here, must minus 1. This is his total waiting time is 9. It's already finished apart. Okay. So average waiting time should be divided by 4. Divided by 4, 6.5. Until here is a primitive shortest of first lane. Until here is a
Right, I just wanted to check with the waiting time, why are we like 1 and 2 and 3, just back to the waiting time, why are we back to?
sorry.
With the waiting time,
Yeah.
why are we subtracting? I missed that part.
Then you do minus.
Yeah.
Minus sign. Because arriving time is different. Which waiting with you arrive. So P2 is arrive at 1 second. And it run at immediately. So it should be P2 is 1 minus 1. Alright, minus is the arriving time. Good?
I think so.
Good. And P1 is difficult and P1 is split two parts. So the waiting time should be this is 0, this is 10, add time together and still minus this part is already finished. So we must minus that. So the average waiting time is good. Average waiting time is good. I think it's optimal. Still much better than non-primitive version. Much better than non-primitive. Again, this is a theoretically result. We cannot reach that because we cannot predict the future. We can know some global information, like you said, time complexity of some algorithm. Oh, this algorithm is running very long. We can make a predict. Oh, then the P1 should be very long. First time should be not specifically 8. Make a range like from 5 to 10, from 10 to 20, not in a range. And the real burst time, you know the real burst time is master after it's running. You know the burst time. Okay. This is this is the details how can we calculate that. I already explained that. If you cannot understand it, read this carefully. And check the textbook or ask me. Oh, next one, priority scheduling. This is much easier to explain. It's a priority. So each of the process or thread have an integer. It's a priority. Smaller means highest priority. It's like our UI, highest priority. Highest priority. Priority scheduling can be also have two versions: primitive version and the non-primitive version. Non-primitive version, two versions. Non-primitive version. The problem is that this priority scheduler looks very good, but the problem is starvations. Low priority process may never execute, so the low priority. You are in the low priority. Okay, waiting for the CPU. But the CPU always has a higher priority count. You never have a chance to execute. That is starvations. This is starvations. They're not good. And the agent, as time process, as timer progressing increase, the priority of the process. The solution is you can use the agent. If you're waiting too long time, we can increase your priority. It's a good idea. Increase the priority. Let's say this. First time priority. So they come same time. They come into the same time. So you have the priority. So execution is based on their priority. Some important work we put into the head. So this integer, if it's smaller, it means a higher priority. Higher priority. This scheduling, it must need a sorting. It must in the sorting in the scheduler. Yeah, sorting this priority. That's why I say sorting algorithm is important. It's used everywhere. It needs sorting. Okay, the average runtime is now you know how to calculate that. Average waiting time. Now you know how to calculate that, right? Okay, any question here? No?
I was thinking like back in the point, I was like earlier, like smallest time, like first, you said another real world process is kind of hard to predict. I was talking with time complexity, what if you also trying to maybe, would be possible to maybe incorporate, like, say if it's like a process that's run like a lot, but if you keep like a log of like, with like a log of priority for that process.
Good idea.
In order for it to.
I know you have lots of ideas. So later I put lots of paper as a future reading. Seriously. Keep in mind is the executive law. So the CPU must write something. It's a big CPU running time. And the scheduling is a bottom layer. It's important fundamental. It must be efficient. Any kinds of you must keep a lot in a where it must be in a memory, not in the file. In the file it's impossible. It has IO operations in the memory. But the memory read and write is slower than what? Than cache. And than register. Right? This is you must think about it as a system. Not this question, not scheduling.
So that's why it wouldn't be good.
Yeah, that's why I say I put lots of papers later. See you later. Read that paper. Okay. Okay. I don't think you have questions here. Calculate the waiting time. Okay, let's go. Okay. Round robin. Round robin is still first come, first serve. You remember first come, first serve, the easiest ones. You come first, serve your first. And now it's a primitive version. Let's add a quantum queue. A quantum queue is a minimum unit. Quantum queue, the minimum unit. After the time has extended, the process is primitive and added to the end of the ready queue. So after this quantum queue is the process not finished, this process is split into two parts and all the other parts added to the queue. So the timer it must be has a timer. A timer to know when is the queue, is arrived. The timer interrupt every quantum to schedule next process. This is the primitive scheduling. And quantum here I say the quantum there and multiple queue as 4. So 4. The quantum cannot be too large. If the quantum is too large, it's reduced to non-primitive. Right? Let's say the quantum to 100, it's mean that it becomes non-primitive. If the quantum is too small, you see the CPU is always busy with split the task. For example, this is quantum at 0.1. Always split the task. CPU split the task that don't make any progress. CPU the computer resource waste. So the quantum cannot be too large, it cannot be too small. I guess 4 here is good. You can set as 2. Right? You can set as 2. 2 is not very bad. 2, 3, 4 not very bad, but 0.1 is too bad. Right? Okay. So the first time, so the P1 running first lane 4. Oh, okay. The quantum terminate. This quantum terminate. So the CPU will switch to P2, but P1 is not finished. P1 not finished. All the other part will be put into the queue. Put the queue here. Put the queue here. And then the P2 is less than the quantum. Okay, it can finish. P3 less than the quantum can finish. All the other part is the P1. P1 is the subject to the each as the 4 is the quantum. 4 is quantum until they end. Looks good. Looks good, and it's typically it's a higher average turnaround than SGF. I say SGF shortest job first is the optimized version. It's you cannot reach. That's why we never have some implementation of a startup first. Does anyone tell you, oh, I implement the startup job quickly? It's a fake. It must be fake. That means we can predict the future. And this quantum version for first come first serve is a better response. It's much better than other ones, and it can be supported in hardware. So CPU can design some hardware to physically support this. Highly efficient. Highly efficient. Okay, here. Important thing is how can we select the queue? Not too large, not too small. Yes. Important thing is the contact switch. Contact switch happens here. Each of the quantum has a contact switch.
That's a question. So looking at the time quantum, that just means like that's like how long the process can run full before it contact switches. Is that what that basically is?
What?
I'm confused about like so time quantity sport. So that means like 4
It's on
other units of time. That's how long like the process is able to run for before it contact switches the process.
No. Contact switch means the CPU exactly here, from here. From P1 to P2, it needs a contact switch. So the CPU must save the status of P1 into PCB, and loading the state of P2 is the PCB. This is called the contact switch. It's need time.
What I was saying is like when it like after like time quantum from like looking at it, it's like 14, like 18, right? That's 4 units of time that we got. But it's still continuing the same process.
Oh,
It's like because like
it don't balance of any type of contact switch.
yeah, it just keeps continuing.
Keep continue. So this can save the contact switch time. So the contact switch need time. 10 microseconds. It looks fast.
You have Q is just an arbitrary time quantum, and then you talk about milliseconds is, so what is Q in terms of milliseconds? So like, because we have milliseconds should be like between 10 to 100. Is that something that's arbitrary? So what is Q in actual time? Is it like 50 milliseconds? Is it 45 milliseconds? What is Q?
What is Q?
Because you say Q is equal to 4.
This is in the morning operating system. In the operating system, they always set the Q at this range. As I said, the Q cannot be too small and too large. So in modern operating system, they set this here because the contact switch need times. It takes 10 microseconds.
Okay, so the operating system sets the Q time.
Yes, you cannot set by yourself. It's an operating system, or the CPU, or has hardware to support this. You cannot set by yourself.
I mean, in this case, are we saying 4 milliseconds? Is that what we're discussing right here?
Right?
I mean, from the looks of it, with our Q equals 4, are we just saying it's just 4 milliseconds?
For this example,
Yeah.
this is example. For
That's what I'm saying, like for the example you're
For
saying.
example, I would say the time unit. It can be milliseconds or can be seconds. It's a time unit. Do you know? But in a real operating system, it's a time unit that should be milliseconds. Here, millisecond here. Okay. CPU is really fast. Okay. The Q. How can we select the Q? here. Good. I think we already finished this topic. Okay. We have 2 minutes left. We already finished most of part of the this okay, the multi-level queue scheduling. So in real operating system, all of us, the strategy always combine together, not single ones. Use a multi-level queue and multi-level feedback queue scheduling. So looks complicated, but the idea is the same as our previous discussed. They may be using all the strategies, they may be together, combined together, make it complicated, and make it suitable for different user cases. Right. Okay, let's discuss this next class. That's for today's class. Any questions that come to my office, or I can stay at until 11:30. Yeah.
First, what, because we have to test the midterm coming, right? Is all of this going to be on the midterm or maybe, do we know when the information?
All of this, all of it discussing in the class. Midterm.
And then will you have a review session before the midterm?
Midterm don't have us, but you know, I put lots of questions in the assignments in the lab assignment.
So if we do the labs and assignment well.
I think you are good. Yeah, good. Assignment I have a part one. You have lots of questions. I will cover. I try my best to cover all the things in the assignments, the lab,
Okay.
and something I think is important. Yeah.
Okay.
Yeah.
So that brings me to another question on the assignment, the first assignment. The last part, like there was, like I found it very difficult. So a lot of the coding I thought it was beyond what we did in the lecture.
Yeah.
Is that typical? Is that something we should be doing a lot of research outside of class?
Yes.
I had to watch
yes,
videos, I had to do, you know.
Yes, because our class cannot cover too much of programming. We're not a programming course. Yeah, you should check from outside. But that part, the midterm and final only cover the basic things. Like ask you what is that? What is the scheduling?
Okay. So there won't be any coding, you have to write something.
Paper coding. Paper
But,
coding.
but would you be very specific about syntax or is it just concepts?
No, we never test your syntax. We test your understanding.
Okay.
If you understanding.
Okay.
Any kind of style is acceptable.
I was wondering, I thought there was gonna be a quiz today. Has there actually been any quizzes yet? Cause I did miss like one lecture. I'm just wondering, has there been like an A-class quiz?
This is the first class.
Yeah, I'm just saying, has there been one or no?
Is asking if there's a quiz, if there's been a
Quiz?
Yeah, has there been?
No, until now, no.
Okay.
Quiz?
I was just making sure I didn't miss one. I was like, it's already like fourth.
A quiz is random. I never tell you when time is quiz.
Oh, no, I'm saying,
Until you come here.
I think it might be next week though, cause there
No.
wasn't this week, but.
No, okay, I think next time I can make some quiz. Okay.
Yeah,
Any question?
Yeah, I was gonna talk about my assignment one.
Mm.
Because I'm already done, but my computer's